This is Professor Upfer, and we're looking at the fourth part of the psychology of reasoning, where we'll cover the topic of induction. We looked last time at deductive reasoning, claims of the form all men are mortal, Socrates is a man, therefore Socrates is mortal. Here we saw that reasoning is a process of integrating certain arguments or certain propositions into a general argument. Here, the propositions go from the most general, all men are mortal, to the most specific, Socrates is mortal. But whether or not this is a valid inference depends on the form of the argument. Whether or not it's true that Socrates is mortal depends on whether the major premise is true. Are all men really mortal? And the question is, how do we know? How do we know whether or not all men are mortal? To get to a premise like all men are mortal, we have to engage in something else. We have to engage in inductive reasoning. Inductive reasoning is the reverse of deductive reasoning in that we reason from the specific to the general. There's probably no better example of a good inductive reasoner than Sherlock Holmes. He provides a very nice example of inductive reasoning in the novels and television shows that are based on the fictional character. In these stories, he often takes very specific clues, or in some cases, a lack of clues, to induce a strong, probable, cogent theory that would be a general case of which all the individual specifics are leading. Now, Sherlock Holmes was a really good inductive reasoner, but his partner, Dr. Watson, wasn't always such a great inductive reasoner. Dr. Watson was, to put it mildly, the Evel Knievel of jumping to conclusions. He might say, come across a scene of a crime, or maybe it's a crime, maybe not. Let's suppose that it's a house where the door is ajar. And Dr. Watson would jump to the conclusion that there's a burglar in the house. If you asked him to explain his reasoning, it might go something like this. If a burglar is in the house, then the door will be ajar. The door is ajar, therefore a burglar is in the house. This is exceptionally weak inductive reasoning. If you think about it, whether or not there is a burglar in the house, given that the door is ajar, depends on a little bit more than just those two facts. A strong inductive reasoning would be the way that Sherlock Holmes would do it. He'd say, well, the probability that a burglar is in the house, given that the door is ajar, is something between 0 and 1. And it'll depend on a couple other probabilities. It'll depend on the probability that the door is ajar, given that the burglar is in the house. After all, sometimes a burglar might close the door behind them. So we can't assume that that's 0 or 1. We'll need to know something about the probability that the door is ajar. People other than burglars leave the door ajar. Some people more, some people less. And we'll need to know something about the probability that the door is not ajar. That'll just be 1 minus the probability that the door is ajar. And so if we want to know what the probability of the burglar being in the house, given that the door is ajar, that is, the posterior probability given all the other facts, we first need to know something about the conditional probability of the house being ajar, given that the burglar is in the house, and the two prior probabilities, the probability that the door is always ajar. And we can combine these things together in a strong inductive reasoning by means of Bayes' theorem. Bayes' theorem states that the probability that a burglar is in the house, given that the door is ajar, is equal to the probability that the door is ajar, given that a burglar is in the house, times the probability that the door is ajar, divided by the probability that the door is ajar, given that a burglar is in the house, times the probability that the door is ajar, plus the probability that the door is ajar, given that a burglar is not in the house, times the probability that the door is not ajar. That would be strong inductive reasoning. But fortunately, children and adults often fail to apply strong inductive reasoning. Instead, what we see is they're often subject to certain biases. We'll talk about a few of those biases or fallacies of inductive reasoning today. They include the confirmation bias, a faulty use of heuristics, a faulty use of representativeness, a faulty use of availability, and a susceptibility to mental sets. And I'll try to illustrate each of these by means of a given problem that we might try to solve. So let's take the first example. Suppose you have to decide what is going to be the next number in a series. All right, so we have 18, 16, 14, and you have to guess what the next two numbers are. Now, this is a case of inductive reasoning. You might induce a general rule, like decrease by 2. You do this by taking the specific numbers 18, 16, and 14 and theorize some general rule, like decrease by 2, that would hold for the known cases and the unknown cases equally. If that was the rule that you used, you would correctly see that the numbers I covered up were 12 and 10. So the rule that you came up with in that case is correct. Now let's take a new case. Suppose I have this series of numbers, 2, 4, 6, 8, and a whole bunch of other new numbers. Now, your job is to predict the other numbers in the series. And to do this, you can ask me about two numbers, and I'll tell you if they're there. Now, you can't do this right now, but think about what two numbers you might ask me about if you could ask me about them. Many people ask me about 10 and 12, and I can tell you that those numbers are in the series. 10 and 12 are in the series. Now, what are the other numbers in the series? Well, these are the numbers in the series. Now, if that's not what you were expecting, all right, then you probably weren't asking me about the right numbers. I'm going to guess that you were expecting that the next numbers would be 10, 12, 14, 16, 18, 20, 22, 24, and so on. And by asking me about 10 and 12, you asked me about positive cases that conformed to your pre-existing theory, but you didn't ask me about negative cases that would disconfirm your theory. If you asked me about 10 and 12, it would, yes, confirm the theory that the numbers are increasing by 2. But it wouldn't allow you to test an alternative theory, which is that the numbers were just increasing. That's a very common problem in inductive reasoning. It's known as the confirmation bias. Common example of the confirmation bias, or only searching for information that confirms one's hypothesis, would be, say, reading newspaper columnists who agree with our point of view and avoiding those who don't. Lots of people understand that that's not being objective. But it's much broader than that. It's also looking for positive evidence for our claim and not looking out for negative evidence that would refute it. In order to induce things, reliably, we need to look for positive evidence and negative evidence with approximately the same vigor. And people don't do that. Another thing that we see in problem solving is we see that people often use one of two methods. One method, say the rule you should always search for positive and negative evidence with equal vigor, is an example of an algorithm. It's a rule that, if followed correctly, will eventually solve the problem. In contrast, people often use what are known as heuristics. Heuristics are shortcuts. They're faster and they work most of the time, but they don't necessarily lead to a solution. Here's an example of a problem. Suppose you're playing Scrabble and you need to start a new word with a Q. What words might you make? Okay, well, if you're using an algorithm, what you'd have to do is you'd have to go through every single possible letter combination and determine if it were a word you could play. So you might start with QA, and then QB, and then QC. Now, this would take a very long time, but you would end up with a solution. It's guaranteed to give you a solution. The other method that you might use is an heuristic. So you might say, well, let's assume that the letter is U, because most words that start with Q have U as the second letter. And you might assume then further that the third letter has to be a vowel, because it's also true that most of the words that start with QU have a vowel as the third letter. Well, now the heuristic is going to give you probably a whole bunch of words that will come to mind quickly. Words like quack, and queen, and quit, and quotidian, and so on. But you're going to miss some words, right? You'd miss chi, cat, cheese, cadi, cade, cats, kof, kanat, and so on. I think these might be the only exceptions. I only know about these because I used an algorithm. Let's consider a different kind of problem. Let's suppose that you have to guess the probabilities of a certain number of events. All right? So guess how many people each year die from heart disease, floods, plane crashes, asthma, tornadoes. Okay, well, as a matter of fact, the approximate death rates per year in the US, at least the last time I looked this up, is that for heart disease, there are 960,592 deaths. For flash floods, it's 108. For plane crashes, it's 147. For asthma, it's 5,000. And for tornadoes, it's 52. Now, the fact of the matter is that these are not what people normally estimate. So in general, people dramatically overestimate the number of deaths from natural disasters or accidents and underestimate the deaths from asthma. Most people say that more people die each year from floods or tornadoes or plane crashes than asthma, even though about 16 times as many people in the US die from asthma each year than die from floods, tornadoes, and plane crashes combined. What people are doing is they seem to be making use of another heuristic known as the availability heuristic. So most people overestimate deaths from natural disasters because disasters occur frequently on television and newspapers and on our Facebook pages. All right? But things like asthma don't make the local news, and they're much less likely to make blogs and things like that. The availability heuristic involves judging the probability of an event by how easily you can recall previous occurrences of that event. And that's extremely subjective because how easily you can recall something will depend on how much somebody else decided it was noteworthy and worth talking about, and not based on its actual events. Here's another example of an heuristic we use. Let's talk about Chris for a second. So Chris is 6'7", 300 pounds, has 12 tattoos, was a champion pro wrestler, owns 9 pit bulls, and has been arrested for beating a man with a chain. Is Chris more likely to be a man or a woman? Is Chris, he or she, more likely to be a motorcycle gang member or a priest? Now, if you think about how you arrived at your decision, it's probably that you had an image in your mind of what this person with these traits were like, and you had a lot easier time imagining this person as a motorcycle gang member and as a man. That's what's known as the representativeness heuristic. So it seems that this person is representative of the class of male motorcycle gang members. Now, that seems like it might be an okay inference. It's not even entirely clear that that violates Bayesian reasoning. But let's try a slightly different problem, one that's similar to it. This is a story about Steve. All right. Steve is meek and tidy. He has a passion for detail, is helpful to people, but has little real interest in other people or real-world issues. Is Steve more likely to be a librarian or a salesperson? Well, if you are like most people, you say that Steve is more likely to be a librarian. Your mental image of what a librarian is might involve being introverted, having a passion for detail, but not being, say, a people person who wants to hang out with other people the way salespeople do. But the problem with this is that if you think about the probability of an event based on how well it matches your prototype, you're missing something important in Bayesian reasoning. So this can be good, but it can also lead to errors. People overuse representativeness. So Steve's description fits our vision of a librarian. But what we should be using are what are known as base rates. All right, so the base rate is the probability that an event will occur or fall into a certain category. So you need to stop and think that there are a lot more salespeople in the world than librarians. So how many people are involved in sales? Well, probably at every store there's somebody who's involved in sales. How many people are librarians? Well, how many libraries are there? There are a lot more places where people sell stuff than there are libraries. So there's got to be way more people who are salespeople than who are librarians. And so when stopping to think about how likely it is that Steve is a salesperson for a librarian, maybe he's an unusual salesperson, but given how many salespeople there are, it's probably a bit more likely that Steve is a salesperson. But very few people take this into account. Now let's consider another problem. It's a chess problem. So 2 grandmasters played 5 games of chess. Each one won the same number of games and lost the same number of games. And there were no draws in any of the games. How could this be? Well, the solution is that they didn't play each other. Okay, let me give you a different problem. This is a bar problem. So a man walked into a bar and asked for a drink. The man behind the bar pulled out a gun and shot the man. Why should this be so? Well, it's because the man behind the bar wasn't a bartender. He was a robber. Okay, one last example. All right. This is what's known as the 9 dots problem. All right. So without lifting your pencil or retracing any of the line, think about how you might draw 4 straight lines that connect all 9 dots. Now, to solve this kind of problem, which you can stop the video and try on your own, in order to solve the problem, you have to do something like this, where you draw the lines outside of the box of dots. This is what people are referring to when they say think outside the box, a phrase that has become so common it kind of makes me want to throw up. But it's based on something important, all right? And that is, to think outside the box refers to trying to break our mental set, all right? So a mental set is a well-established habit of thinking, and it interferes with problem solving. So if you think about the problem with the chess, you're probably in the mental set of thinking that 2 chess players would be playing each other. Or if you're thinking about the bar problem, you're thinking that the man standing behind the bar is likely to be the bartender, and the person who's on the other side of the bar is likely to be a customer. And the same way with the dots is you're probably in the habit of thinking that the solution has to lie within the box rather than outside the box. There are a number of ways that mental sets play a role in interfering with our reasoning. One example of this is a particular kind of mental set that's known as functional fixedness. All right. This was first explored by the psychologists Dunker and Dunker. They asked people if they could use the materials that you see in this picture, all right, such that they could make the candle lit and standing up against the corkboard, but without burning it. Now, this is not a problem that 100% of people solve correctly. Only about 25% of people could solve this problem, just as it is here. One kind of solution that people would do who did solve the problem is they'd provide a solution like this, where they'd tack the box of thumbtacks against the board using the thumbtacks, and then they would plop the candle on top of the box and light it. Now, this kind of problem is one that requires some creativity. And what Dunker and Dunker found is a way of reducing people's creativity. So in one condition, what they did is they began the task by asking people, what is this box of thumbtacks for? And they'd say, well, to hold the thumbtacks. And what are thumbtacks for? And they'd say, well, to put pieces of paper against the corkboard. And what's a candle for? To light things. What's a box of matches for? Well, it's to light the candle. And when people started by thinking about what the function of the objects were explicitly like this, it led them to not see creative uses of these same items. And it induced a mental set. So this is another sort of problem that we see, where by inducing a habitual way of thinking about things, we actually interfere with our ability to think about things in new ways. Okay, so in conclusion, I think we've seen that reasoning is not an innate automatic process. Psychologically, rationality requires well-formed concepts and explicit use of quantifiers, the ability to visualize complex relationships, the ability to apply quantitative knowledge over our pre-existing theories, and to apply quantitative knowledge over fast and easy problem-solving strategies. In short, reasoning is work. But it's the only method we have for gaining knowledge and reducing uncertainty. And so I'd just like to leave you with something that the Enlightenment philosopher Spinoza said, which I think applies really well to reasoning as well as many other things. And that is that all things excellent are as difficult as they are rare. So even though reasoning is excellent, we shouldn't be too surprised when it doesn't show up as often as we'd like to see it. Thank you.